I'm Rebecca Barnes and welcome to the first Science at Easter podcast. I will be your host on this journey of discovery into the rapidly evolving field of space astronomy and planetary exploration. For millennia, humankind has been fascinated with the night sky. Our thirst for knowledge and understanding has driven us to study the movements of the stars and planets. Astronomy has played an important part in everyone's lives for at least the last 4,000 years. The invention of the first astronomical telescope 400 years ago took us close to the stars and planets. It completely changed our perception of our place in the universe. But telescopes on Earth only give a limited view. The birth of the space age dramatically opened the eyes of astronomers to a much larger cosmos. By launching astronomical telescopes into space over the last half a century, we now know that the world in which we exist is just a tiny corner of the universe, and that there is much more out in space than meets our naked eye. Telescopes, be it on the ground or in space, gather light. When we hear the word light, we automatically think of what we can see with our eyes. Visible light is one form of electromagnetic radiation. The spectrum of visible light can be seen when white light is passed through a prism, but this is just a small slice of the full spectrum. Light is a wave. That is, electric and magnetic energy fields that are oscillating in phase and at right angles to each other. These waves travel at right angles to both of the fields. Electromagnetic radiation is the way most of the energy in the universe is transported. The different portions of the electromagnetic spectrum are only different in terms of the amount of energy they carry. All of them are waves that move through a vacuum at the speed of light, which is approximately 300,000 kilometers per second. Radiation is a spectrum of light that is not bound by the limitation of our eyes. Light from different objects in space covers the entire frequency range of the electromagnetic spectrum. But this is something astronomers have only been able to observe since the start of the space age. Each new space telescope that has been launched to detect different forms of unseen light has revolutionized astronomers' understanding of the universe. But why has the space age been so important? Why do we need to launch telescopes and observatories into space?
Electromagnetic radiation emitted by celestial objects propagates towards Earth. Detection of this radiation is astronomers' principal bridge to understanding the processes that govern the universe. But much of the light in the electromagnetic spectrum can't penetrate Earth's atmosphere. Fortunately for life on Earth, the dangerous high-energy gamma and X-rays are absorbed by oxygen and nitrogen in the upper atmosphere. Most ultraviolet wavelengths are absorbed by oxygen and ozone molecules in the upper atmosphere and stratosphere, although a few very specific wavelengths do make it through. It's obvious that most visible light can travel through the atmosphere, and so can near-infrared radiation. Most infrared wavelengths are absorbed by water molecules. So it is possible for astronomers to observe in the infrared as long as the location of the observatory is at a high altitude and where humidity is low. The atmosphere is also transparent to most of the microwave and shorter radio wavelengths.
The opacity of the atmosphere isn't the only problem overcome with space telescopes and observatories. Observing from space means that it is possible to obtain high-precision data of the sky with reduced background noise caused by human activities and natural phenomena. Even the light that can be observed from Earth is distorted as it passes through turbulent layers in the atmosphere. In space, the stars do not twinkle. Light propagates freely. To capture the full picture of the universe around us, astronomers need to evade the barrier of the atmosphere and launch satellites into space. Looking at different types of light coming from objects in space reveals a hidden and violent universe.
This is a typical visible view of the entire sky. Hydrogen atoms in interstellar space emit radio waves, and so in this image, the brightest areas show where most of the hydrogen is. In this case, it is in the plane of the Milky Way. Infrared light is emitted by dust particles. Here, we see the vast amounts of dust found in space between stars in the plane of the Milky Way. The dust emits infrared waves using energy received from nearby stars. gas that is at an extremely high temperature generates X-rays, and fast-moving subatomic particles colliding with nuclei of atoms in interstellar space emit gamma rays.
Early in the 20th century, Einar Hertzsprung and Henry Russell independently created diagrams in which stars are plotted according to their absolute visual magnitude and their spectral type. This is a typical Hertzsprung-Russell diagram, which clearly shows a distribution that is not random. The majority of all stars plotted sit on this belt running across from the top left down to the bottom right. This is known as the main sequence. A main sequence star has reached a stable hydrostatic equilibrium state. Our Sun is a good example and sits here on the main sequence. There is a definite grouping in the top right of the diagram where we find giant stars, with white dwarf stars grouped on the bottom left. The ability to launch satellites into space has provided crucial insight into the life of stars. Protostars form from collapsing gas clouds. On the Hertzsprung-Russell diagram, these infant stars do not appear on the main sequence curve, but take a path known as the Hayashi track as they progress towards the main sequence. Once a protostar becomes a fully fledged star, we find that its position on the main sequence line depends upon its mass.
The famous constellation of Orion, the Hunter. Here we find a giant molecular cloud stretching from Orion's belt to his sword. Visible to the naked eye is an area of this cloud known as M42, the Orion Nebula, an exquisite sight when viewed in visible light. M42 is visible because of young, very hot stars that have formed here, exciting the surrounding hydrogen gas, which glows in the visible part of the electromagnetic spectrum. But using visible light, it is not possible to look inside this beautiful nebula. The gas and dust it contains blocks the view. To explore M42 further, astronomers need to detect longer wavelength electromagnetic radiation, which can pass through the gas and dust. An infrared telescope unveils M42, providing a glimpse of forming stars. It is not only protostars that are found in the Orion Nebula, it also contains a cluster of very young stars. Observation of X-ray emissions from the Orion Nebula have enabled astronomers to discover more about the behavior of Sun-like stars that are just 1 to 10 million years old. These young stars release violent flares that are more energetic and occur more frequently than any seen from our middle-aged Sun.
At the other extremity, a star that is more than 8 times the mass of the Sun evolves from the main sequence on the Hertzsprung-Russell diagram to the region of the supergiants. These massive stars have an explosive end to life, a supernova. M1, or the Crab Nebula, is located in the constellation of Taurus, but is not visible to the naked eye. This intricate, striking nebula is the remnant of a supernova that was so bright it was visible to the naked eye in 1054 AD and recorded by Chinese astronomers of the time.
It's another beautiful nebula in the visible spectrum. Images of the infrared radiation emitted by M1 reveal filament structures that run through this nebula. These are thought to contain hot gases, but their exact nature still remains a mystery. The infrared also shows a cloud of energetic electrons trapped in a magnetic field and emitting synchrotron radiation. What is driving this cloud of electrons is exposed when X-rays emitted by M1 are detected. At the heart of the Crab Nebula, we find the leftovers of the original star, a rapidly spinning neutron star. This pulsar has a mass equivalent to squeezing the Sun into a ball just 20 kilometers across. It is rapidly spinning and spewing out pulses of high-energy radiation 30 times a second. Detecting high-energy X-rays that are emitted from the fast-moving particles in the center of the Crab Nebula allows astronomers to probe deeper into this exotic object.
However, there is much more to these objects than just a pretty picture. After detecting radiation from space, astronomers need to analyze it to uncover clues to help reveal the physical processes occurring inside. One way is to study the spectra of light. This provides astronomers with specific information about the makeup of an object. All chemical elements have their own characteristic signature due to the absorption and emission of light at a particular wavelength. This is not just limited to the visible wavelengths. The unique signatures of different elements can be found right across the electromagnetic spectrum, providing crucial information about the chemical composition of celestial objects. Over the last half a century, scores of satellites have been launched to detect radiation across the entire electromagnetic spectrum.